Hello everyone, welcome in our lecture. Today's topic of discussions, so pharmacodynamic and pharmacokinetic of a drug. So first, pharmacokinetic. What is a pharmacokinetic? Pharmacokinetic is a science of the kinetic of a drug, absorption, distributions and elimination. That is exertions and metabolism. This is the pharmacokinetic. So next, pharmacodynamic. Pharmacodynamic is referred to the relationship between the drug concentrations at the site of actions, receptors and pharmacologic response. This is known as pharmacodynamics. So next, absorption. Absorptions, the process is a movement of unchanged drug from the site of administration to systemic circulation is called as absorption. So absorption in this process is a movement of unchanged the drug from one site of administration to systematic circulation is known as absorption. It can be also defined as the process of movement of unchanged the drug from the site of administration to the site of measurement. That is a plasma. So next, factors affecting the drug absorption. Factors affecting the drug absorption. So first one, A, is a physicochemical factors. So first factor, drug solubility and dissolution rate. Second, particle size and effective surface area. Third, polymorphism and amorphism. Fourth, pseudo-polymorphism. Fifth, salt from of the drug. Sixth, lipophilicity of the drug. Seventh, decay of a drug and gastrointestinal pH. 8. Drug stability. So next, factors B, pharmaceutical factors. So first, distinction times. Second, dissolution time. Third, manufacturing variables. Fourth, pharmaceutical ingredients. Fifth, nature and type of dose from. Sixth, product age and storage conditions. So next, factor C, patient related factors. So first, route of administrations. Second, membrane physiology. Membrane physiology is a two types. So first, A, nature of cell membrane and B, transport process. Third factors, age. Fourth, gastric emptying time. Fifth, intestinal transit time. Sixth, gastroessential pH. 7, disease state. 8, blood flow through the GIT. 9, gastrointestinal contents. Gastrointestinal contents is the first, A, food drug interaction. B, fluids. C, other normal GI contents. 10, pre-systemic metabolism. So first, A is a luminal enzymes. B, gut wall enzymes. C, bacterial enzymes. D, hepatic enzymes. So first one is a factors, is a physicochemical factors. Physicochemical factors is a first, drug solubility and dissolution rate. The rate determining step in absorption of orally administered drug are: first, rate of dissolution, and second, rate of drug permeation through the biomembrane. The dissolution is a rate determining the state for hydrophobic and poorly aqueous soluble of a drug. For example, gyrosoflavins and spironolactone. This is the examples. Second point is a permeation is a rate determining state for hydrophilic and high aqueous soluble drugs. This for examples, cromolyn sodium or nimomycin. So seconds, first drug solubility and dissolution rate. Second, particle size and effective surface area. Particle size may play a major role in a drug absorption. Second point, dissolution rate of solid particles is proportional to the surface area. Third, smaller particle size, greater surface area, then higher will be dissolution rate, because dissolution is throughout takes place at the surface area of the solute. Next, the particle size is a reduction has been used to increase the absorption of a large number of poorly soluble drugs. For example, bias hydroxyfumarins, digooxin, gyrosoflavin. This is the examples of particle size and effective surface area. This is the two types of the surface area. So first types absolute surface area and second effective surface area. In absorption studies, the effective surface area is of much important than absolute. Next, to increase the effective surface area, we have to reduce the size of particles up to 0.1 micron. So this can be achieved by microorganization process. But in this case, one most important thing to be keep in mind that which type of drug is microorganized if it is. So first type hydrophilic and second hydrophobic. So first one is a hydrophilic. In hydrophilic drugs, the small particles have a higher energy than the bulk of the solid, resulting in a increase the interaction with the solute. And so second be hydrophobic drugs. Hydrophobic drugs in these microorganization techniques result in decreased effective surface area and thus fall in dissolution rate. So third factors, polymorphism and amorphism. So first point, depending upon the internal structures, a solid can exit either in a crystalline or amorphous form. When a substance exits in a more than one crystalline from the solvent form are designated as polymorphs, and the phenomenon is polymorphism. This is the polymorphs are two types. First, enantiotropic polymorph and second monotropic polymorph. So first one is a enantiotropic polymorph is a one which can be reversible changes into another form by altering the temperatures or pressure. For example, sir. So second, monotropic polymorph is the one which is unstable at all the temperature or pressure. For example, glycerol stratates. And this next example, the vitamin riboflavin exit in a several polymorphic form. Polymorphic form is a third of riboflavin is a 20 times more water soluble than the from first. So next, amorphism. Amorphism is a some drug can exit in a amorphous from that is a having no internal crystal structures. Such drug represent the highest energy state. So next, they have a greater aqueous solubility than the crystalline forms because of energy required to transfer a molecule from the crystal lattice is a greater than that required for non-crystallines. Non-crystallines, that is a amorphous form. For examples, the amorphous form of nohobiosine is a 10 times more soluble than the crystalline form. Thus the order of different solid dose from of the drug. Fourth factors, pseudo-polymorphism. Pseudo-polymorphism, when the solvent molecules are entrapped in the crystalline structures of the polymorph, it is known as pseudo-polymorphism. So first, solvent. The stoichiometric type of the adduct where the solvent molecules are incorporated in the crystals. Crystals lattice of the solid are called as solvates and trap the solvent as solvent of crystallizations. So second, hydrates. When the hydrates is a solvent in association with the drug is water, the solvate is known as hydrate. Next point, hydrate are pseudo-polymorphs where hydrate are less soluble and solvent are more soluble and thus affect the absorption accordingly. Fifth factors, salt from a drug. While considering the salt from of the drug, which pH of the diffusion layer is important, not the pH of the bulk of the solutions. So, for examples of a salt of a weak acid. Salt of a weak acid, it increases the pH of the diffusion layer, which promotes the solubility and dissolutions of a weak acid and absorption is bound to be rapid. So next point, other approach to enhance the dissolutions and absorption rate of certain drugs is the formation of in-situ salt formation. That is increasing in a pH of microenvironments of a drug by incorporations of a buffering agent. That is, for examples, aspirin and penicillin. So next factors, pH-Partion hypothesis. The theory states that for the drug compounds of molecular weight more than hundreds, which are primarily transported across the biomembrane. By passive diffusion, the process of absorption is governed by. So first, the dissociation constant pK of a drug. So second, the lipid solubility of the unionized drug. Third, the pH at the absorption site. So next factor 8, drug stability. A drug for oral use may destabilize either during its shelf life or in the GIT. This is the GIT is a gastrointestinal tract. The next, the two major stability problems resulting in a poor bioavailability of an orally administered drug are degradations of the drug into inactive and interaction with one or more different compounds. So either of the dose from or those present in the GIT, gastrointestinal tract, to form a complex that is a poorly soluble or it's unabsorbable. Thank you.